Multi-step synthesis, please look at it. Be looking at that. We'll pick it up a little bit later. Let's look at some miscellaneous things in here. There's also a multi-step synthesis here with the cal at the bottom. Please look at that. There's a puzzle epoxide reactions. It comes with a little riddle. The riddle is, was the sodium atom certain that he had lost an electron? And then you put your letters down here as you answer the questions and you answer the riddle. This is similar to the alkene puzzle I gave you guys on get one. Okay. So, some problems to practice problems there. Over here, use of an epoxide in the synthesis of Prozac. Starting with this molecule here, they make the epoxide. You're going to get the enantiomers. You can separate enantiomers. Okay, we haven't talked about it too much. Organic 1, they separate out this enantiomer. Then they react it with C to get this. What is reagent C? DME is a solvent. Red Al. That's two solvents. Red Al. What is Red Al? Red stands for reduction. Reduction aluminum. It's a common name of a reagent. It's an aluminum reagent. We'll see something like that a little bit later in the course. What I'd like you to look at is what is actually the nucleophile. Okay? What is reacting with this to get this? See if you can rationalize that, and we may look at it a little bit later. While we're here, I point out some other, this is just a good old SN2 reaction. This is a nucleophilic aromatic substitution. We'll be covering that during test 2. This over here is actually something we're looking at right now. They make a mesylate. They turn the OH into a mesylate. You remember that's similar to a tosylate? Now the mesylate can be a good leaving group. And what actually, when they do the SN2, what are they reacting it with? Methylamine. And so they have methylamine. These electrons come in here and kick off the mesylate. Now you have the nitrogen bonded. Nitrogen loses an H to go neutral. But that's how they get the nucleophile on there. So that's some chemistry we should be familiar with. This is coming during test 2. So please be see if you can rationalize what went on there. Lots of applications of epoxides. Here's one here. Have you ever heard of antifungal medications like Lotrimin, Lamisil? These inhibit fungus. The fungus, they target this enzyme. They inhibit squalene epoxidase. The fungus uses these enzymes to eventually synthesize ergosterol. I think ergosterol is important for the fungal cell wall. Okay, if it can't synthesize ergosterol, the fungus is not going to survive. These drugs target this. This enzyme converts squalene to this structure, which has an epoxide. Okay? So epoxidation takes place during this process in the fungus. The drug keeps this from happening. Now from here, this eventually goes on to ergosterol, which is a lot like cholesterol, very similar. But if you look here, there's really no ring system through here. We only have the small epoxide ring. Over here, we now have 4 rings. How in the world does this take place? I kind of show you the mechanism on the other side. It's an epoxide mechanism. It starts with the epoxide. Here's the epoxide. Now there's acid catalyst around and everywhere, or can be in the organism. This is just a magical process to me. Protonate ionized to make tertiary cation. Then from there, this alkene can attack the cation. Now I'm doing it all in one. I don't want to redraw every structure here. So I'm doing it sort of all at once. Cation here. Then this alkene can attack that cation, leaving cation here. Then this alkene can attack that cation, leaving cation here. Actually, it may be up there. I have to look at what size ring. You theoretically predict the cation to be down here. Actually, no. Yeah, down here. You can look at it. This eventually leads to this cation. To get to the final product, you have to do a hydride shift, another hydride shift to get cation over here. And then I believe it eventually beta eliminates to put in a double bond.
Did you say this was not a concerted reaction?
Yeah, I just did it all at once, which probably, you know, cation here, and you redraw. I just didn't want to redraw every single structure. All right, I'm giving you the Cliff Notes version. Okay? Yeah, eventually there's a double bond in here. That comes from eventually you do a beta elimination and slip in a double bond. And that's how your body essentially also makes cholesterol. That four-membered ring system. Okay? It's carbocation chemistry. Again, I abbreviated it. Okay? All right. There's also some questions in the back. These did not make it into the workbook. There's a separate page of epoxide questions, and the answer to these are on the very back, upside down, so you don't look at them until you want to. Okay, NMR. I hope you're looking more and more at NMR. My questions on the NMR warm-up page. Okay. We'll pick up with NMR maybe on Monday. Okay. At this point, though, any questions about NMR? Need to be doing some reading. Okay. We're ready to start looking at the splitting or coupling, why you get some signals, singlets, doublets, triplets, quartets. We'll be reading about that. Looking ahead in the handout. And when I pick back up with it, I'll expect that you have been reading and you're up to speed and you're ready to ask questions, and we'll be moving on.
What are the most common atoms that NMR is done on?
Proton and carbon is by far the most common. Fluorine NMR is routinely done. From there, it gets pretty sort of exotic. I mean, I just saw something with boron NMR. But like we said, you can do NMR on just about any element on the periodic table as long as you have the right isotope and the right instrument. Some don't give NMR signals quite as nice as others because of other effects that are present. Like while fluorine gives a great signal, the other halogens don't give good signals. That's because they're quadrupolar, if you know what that means. There are different spins that nuclei can have. Okay. One other thing about NMR I can point out is on page 23L in the lab manual, there's this assignment for one of the labs, 23L. Okay? We're not doing this lab, but still you can look at this assignment and use it as a practice. Okay? So if you have any questions about it. 23L. Of course, the lab we are doing is the Lucas on 24L. And at this point, any questions about the Lucas for next week? Any questions about lab? Okay. Let's move on to the alcohol oxidation. which will also include alkene oxidations. Now on the green sheet, we've now flipped over to the other side. And we'll see our alcohol oxidations. And then below are your alkene oxidations. And this will be the last material before test 1, okay, which will also include NMR, which we need to finish up. But our board is not ruined. We'll see this similar overview on our other handouts. I'll do the overview here. Essentially, we can take an alcohol, and we'll be oxidizing the alcohol to a carbonyl compound. Okay? We got a C single bond O. Carbonyl has a C double bond O. So we're putting the extra bond between the carbon and the oxygen. We'll learn that a primary alcohol goes to an aldehyde. An aldehyde can be further oxidized to a carboxylic acid. Whereas secondary alcohol is just oxidized to a ketone. And in this class, you cannot further oxidize the ketone. So let's get over to the other two handouts because the material is more clarified there. We have a blue warm-up, and then we had one that I wanted you to print on your own. On the blue warm-up, here's an example of an oxidation. Hormones. This is estradiol. We see the secondary alcohol here. And this molecule here is estrone. Okay? It's an estrogen. What's the difference? Well, the alcohol has been oxidized to the ketone. Now this alcohol oxidation is extremely important. Here's an example of a biological process where you see it. Okay. We'll stick with the blue for now, and then we'll move to the white. The white is more sort of written mechanisms, written things. Okay. The blue is more of our sort of outline. Okay. Primary alcohol can be oxidized to an aldehyde. That can be further oxidized to an acid. We said this on the previous sheet, but let's get into it a little bit more. What's going on when we oxidize? You may have already recognized that here we have two H's, right? When we oxidize, we essentially are removing two H's and putting in the double bond. So minus 2H. Now I'm rotating my oxygen, but this carbon only has one H, and then there's no H on the oxygen. I'll just rotate it. So we're putting in a double bond between here, and to put in the double bond, you have to remove two H's. Same thing down here. Okay, there is one H here. Now here I'm not rotating my carbon-oxygen bond, but if we remove these two H's and then make that a double bond, well, that's what you have, and that happens to be a ketone. Indeed, secondary alcohols do give ketones because there's two R groups here. Where there was only one R group on the carbon that becomes the carbonyl. Now the O in parentheses is generic for just oxidation, or maybe an OX. Might see that sometimes. How do we know this is an oxidation? Now, Gen Chem, when you're dealing with metals and you do redox, you look at oxidation states. Okay? So if iron 2, okay, Fe2 plus, if that goes to Fe3 plus, what type of reaction is it? That's oxidation. You see that because of oxidation states. Now, in terms of electrons, did this gain or lose an electron? Okay? It lost an electron. It's oxidation. And you know the mnemonic, what? Oil rig, oxidation is loss, reduction is gain. Okay? Well, that really only works when you're doing oxidation states. Here we're not really doing oxidation states, and you don't usually do that in organic chemistry. In organic chemistry, there's two main ways to judge redox. If you lose H's, that's an oxidation. Correspondingly, if we gain H's, that's a reduction. Okay? Now in organic 1, when we hydrogenated an alkene, right? You take this alkene and react it with H2, and like palladium, what do you get? The alkane. We've added H's to the alkane. I mean, we've added H's here. So this is a what? Reduction. Okay? And often you say you reduce the alkene. Okay? If you add H's, here we're removing H's, so it's an oxidation. Another way to judge redox in organic chemistry is number of bonds to a more electronegative atom. For the carbon, how many bonds to a more electronegative atom does this carbon have? 1. How many bonds to a more electronegative atom does this carbon have? 2. It has more bonds to a more electronegative atom. That is considered an oxidation. Okay? So, there we go. Now, tertiary alcohols, because there's no H here, you cannot oxidize them in this place. Okay? No basic oxidation here. Because you can't make you can't have 5 bonds here. You'd have to lose an R group, and you're not going to do that in this class. Okay. Now, how do you do this? This is done with common oxidizing metal reagents, such as sodium dichromate or potassium dichromate, or chromium trioxide or KMnO4, potassium permanganate. These are common oxidizing agents that you saw in Gen Chem. They will do this to alcohols. I call these the big 3, considering these are the same, just a different cation. So dichromate, chromium trioxide, or KMnO4, I call them big 3. I'll use that terminology more and more. Mechanism, how does this happen? Let's look over on the white sheet. Usually these are used with acid, okay? Such as sulfuric acid or acetic acid. Ultimately, the chromium is going to lose some oxygen. How do you make oxygen a better leaving group? Chrominate with acid. Well, that's kind of why we're using acid, because it all kind of helps get that idea. Now, these two, I'm not going to show you details about this one. It all works. Both of these, in the presence of aqueous acid, actually become the same thing. They become chromic acid. All right? And chromic acid will oxidize the primary and secondary alcohol. These will come together to react. The alcohol will be converted to a carbonyl compound. The chromium, since the alcohol is oxidized, what's going to happen to the chromium?
To be reduced.
To be reduced, okay? It is actually reduced to chromium, well, it's first reduced to chromium 4. This is chromium 6. It's orange. It's actually a 2-electron reduction. It goes to chromium 4. Problem is, chromium 4 is not stable, and this immediately goes down to chromium 3 by an auto-redox reaction that's separate from your carbonyl compound. Ultimately, the fate of your chromium 6 is it becomes chromium 3. So it's clearly reduced from where it started. Chromium 3, it turns out, is blue. That, thus, gives us a visual test that we can use. Whenever you do this reaction, your orange typically becomes blue. Your orange reaction will become blue. And that will tell you that the reaction took place. That's actually the basis of the Jones oxidation test. A primary or secondary alcohol will turn orange chromic acid to blue. You can see that. But a tertiary alcohol, which is not oxidizable, does not. Tertiary alcohol will not reduce the chromium. So this is a common test to determine perhaps what type of alcohol you have. This complements, what was the other test we had? The Lucas. Sort of complements that. Okay? Now we've got to be careful because aldehydes also give a positive Jones oxidation test because alcohols can be oxidized by chromium as well, or aldehydes can be oxidized by chromium as well. Okay, so let's look at an example down below. You take this alcohol, react it with chromium trioxide with some type of acid. We're going to get, wait a minute, carboxylic acid. How in the world do we get that? How in the world do we get that? A little bit cumbersome going back to the two handouts. But if you go back over here, primary alcohol gives aldehyde. Aldehydes are susceptible to further oxidation by these reagents to give carboxylic acid. Now what's going on there? Are we removing H's? We're actually not removing H's. What are we doing? We're just adding in oxygen. Well, that's an oxidation. It's a different type of oxidation. Now we actually are removing H's because the mechanism here is this needs water. Okay? This reacts with water to give what's called a hydrate. Hydrate. And we'll be seeing hydrates during test 4, okay, way over in like April. That's just where you add water. That's not a redox reaction. How do we know it's not a redox reaction? We added oxygen, you may be thinking, hey, it looks like redox. We added more than just oxygen. Look at this. How many bonds does this carbon have to a more electronegative atom? How about that one? 2. See, there's no change. Okay? That was not redox. But now, what if we remove these two H's here? And put a double bond in between the C and the O. What do we get? Well, we get that. We now have a double bond between the C and the O, and you got an OH left. So there's actually your oxidation. The take home is primary alcohols, if you use the big three, go all the way to the carboxylic acid. Secondary alcohols stop at the ketone, you cannot further oxidize them. So now we can look at these examples. Take this alcohol, big three. What does a big three do to a primary alcohol? All the way to the carboxylic acid. Okay? There's your line reaction. There's your note card information. There's your, this is a standard reaction in organic chemistry. Now, what if you want to stop at the aldehyde, that intermediate? You cannot do it with the big three. You will not stop there. But you can stop there with something called PCC. And this is in a dry solvent. Okay? PCC is this guy here. It is a chromium reagent. PCC stands for pyridinium. That's a pyridine ring protein. Pyridinium chlorochromate. Okay? That's it here. The difference is, though, this is dry, where your big three are typically done aqueous. They have water. And the water is important because what does water do to the aldehyde? It converts it to the hydrate, and the hydrate gets oxidized. If you don't have water, this is not going to convert to the hydrate. This is also a little milder. This reagent, because it's got this organic portion, is actually soluble in organic solvents. And you can do it dry. Where something like chromium trioxide is, you have to have water there essentially. So if you want to stop at the aldehyde, PCC. Now aldehydes can be further oxidized. That's what we did up top, yeah? Now you can use a big three. That'll take it all the way. But there is a unique reagent that's just usually done here, and that's silver ion. Silver ion will oxidize the aldehyde to the carboxylic acid. And something we can say about that is silver does not oxidize alcohols. So silver won't oxidize this, but it will oxidize that. And this is actually a common, well, let me say it like this. You ever hear silver ion? Majority of the time, it's probably referring to this reaction right here. Okay, we're not going to see silver ion do much else. Now, this is being oxidized. What's being reduced here? Silver ion is being reduced, and if you reduce it, it becomes what? It becomes silver metal. It goes down to silver metal. And when you do this reaction, the silver metal will appear in your flask because it will no longer be soluble. And it will actually look like a mirror, sometimes called a silver mirror. And if it separates nicely and it's a thin coat, you can actually maybe see your reflection in the silver. Okay. But usually it's kind of dark or it doesn't do that. But we actually have another chemical test. And that's called the Tollens test. The Tollens test is where you use silver. By the way, ammonium hydroxide is used to help solubilize the silver ion. The Tollens test is a test for aldehydes. This only works with aldehydes. For example, the Tollens will distinguish between an aldehyde and ketone. Because the silver ion will oxidize an aldehyde, but it will do nothing to a ketone. When this takes place, the silver is reduced to the metal, and you see that silver mirror. If it's a ketone, you don't get the silver, because nothing happens. It stays soluble silver ion. That's actually our third chemical test. Now, of course, down here I have an example of a secondary alcohol. One of the big three, what is it going to give? Ketone. Now, you can also use PCC to do this. But that's kind of a waste of money, because PCC is a little bit more expensive. And the big three do this nicely because that can't be further oxidized. Okay? Please look at this sheet. We'll finish up some miscellaneous things up there. We'll be moving on